Yeah.
So I will welcome question from the audience.
Yes.
Maybe we're also going to have some questions from Korea, I believe. So I hope that will work. I'd like to start maybe asking one question to Prof. Sastise-Karan. So we see the multidisciplinary approach that you're using, and that is very nicely shown. But from a teaching perspective, how do you see the challenge of educating young students, they're here in the audience, with a solid multidisciplinary knowledge in life, physical, and engineering sciences? In other words, do you think there's a danger of providing a kind of superficial knowledge to trying to cover all of them at the undergraduate level? So how do you address this as a professor, as a teachers?
I think that's an excellent question. That's something that we have taken fairly seriously, and I can give you specific examples of how when you're looking at curriculum at the interface of, let's say, life sciences engineering, and biological engineering is a perfect example at MIT, that we had to sort of walk the talk, if you will, in terms of this paradigm. It's how I truly believe that at the end of the day, we cannot rehash old curriculum and teach things in a superficial way, but you truly need, at least from the generation that we're a part of, there's an engineer and a life scientist to teach together. Hopefully, the future generation that's able to have both the rigor of the scientific principle, but more importantly, the types of engineering thinking that's needed to solve these types of problems. So we have to really walk the talk in the curriculum as deep as possible in terms of making sure that both components are seriously thought with the level of depth and rigor, so that we're able to build on that in a much more meaningful way, so that the next generation would have individuals that have both foundations.
Thank you. Professor Ying, you have something to add about this maybe? Or?
Yes, I think the basis for a lot of the work that we do are really interdisciplinary in nature. So for us, as a research institute, we don't really have departmental boundaries. We have researchers who come from science background, engineering background, and medical background working together on projects. So we are really project-oriented. To tackle the different challenges of the project, we will assemble a team according to what expertise is needed.
Thank you. All right, so any question from the audience, from the younger people? We have over here. Go to the microphone, please.
Hello. Hello.
Oh, we have Hanamaseo, Korea. Hello. Okay, so maybe we start with Korea first, and then we have our in here. So please, answer your question.
So my name is Won Go. I'm from Yangjeong High School. Before the question, it is great that you are joining us at Molecular Symposium through the internet. Please don't forget that we are here as one of your audiences. I think my question is that I think it is very hard to describe the motion and interaction between nano-sized materials with Newtonian mechanics. Is there any new method other than Newtonian mechanics?
Oh. Is there any method than Newtonian mechanics? I guess that's a question for you. That's a tough one.
Usually we are dealing with these materials as solids. Yeah, so this is what we are working on. So these materials obviously have interesting properties. The quantum confinement effects is very different from what you see in the bulk solids. So.
Is there other insight from over there? Yes, please. Go ahead.
I am Shin Jung-yeon from Ihwa Girls High School, and I have a simple question for Professor Ying about, do you believe that in the near future, through nanocomposites and nanotechnology, we would be able to cure diseases that were once considered incurable, like cancer?
So yeah, as you know, the work with trying to tackle cancer has been going on for many years, and this is really a very complicated problem. and I think that there is some things that nanomedicine can do, for example, to minimize some of the side effects that is associated with chemotherapeutic treatments. But fundamentally, there's still a lot more to be learned about how one can detect cancer at the earlier stage and how one should go about treating the cancer with better drugs. So there's still a lot of things that need to happen, and with both the diagnostics and the treatment aspects. And I think it will take a very long time, unfortunately, with all the medical fields. Yeah.
I'm happy to add my perspective. I truly believe nanotechnology, particularly nano delivery, such as what Dr. Ying spoke earlier, truly would advance the treatment options, especially with regard to either combination and, as you said, particularly in the context of side effects. So I think whether we'll have a cure or not in a broad sense is something one needs to see, but I think there are going to be some, what I would call as low-hanging fruit opportunities, where there will be clear differentiating factors that would make this an important avenue for the future.
Thank you. Thank you very much. Thank you. 감사합니다.
Thank you.
All right. So we have a speaker question here from the audience.
My name is Sanghyun Nam from Korea, Yangjeong High School.
Okay, they sneak in here too.
Yes. Before I ask you a question, please understand that my English conversation skill is not good. I hope that you two professors give me some advice. I want to be a robot scientist, so I want to make a robot, especially a micro robot, which can destroy virus or bacteria in human body. This robot science field is not advanced well, so I want to lead this field. And so the question is, what things do I have to consider to make a micro robot? This consider means like what materials to use to make this robot, or what process to detect virus, and etc. Yes.
That's a tough one. So you want to make a robot that basically cure a lot of different things, right?
Yes.
Do you have any ideas in there?
There's obviously a lot of interest in this area, and there are great advances in making these tiny robots that can go into our body. And right now, for example, there are things that go into our body to take pictures to try to detect sources for cancer, for example. And there are also devices we put into our body to do drug delivery in the form of stents, etc. So there are lots of different things that one can do. Still a lot of challenges, but it is a very fertile area for doing various research.
Thank you.
Thank you very much.
Anyone else? Here, over here.
Can I ask a question?
Microphone. Oh, sorry, just here first, and then over there. Please go to the microphone.
Good afternoon, speakers, and I'm Akash from Catholic Junior College, and my this question is a bit general. The two speakers talked about how many disciplines should work together. So my question is it possible in the future to use nanotechnology and biology to study cosmology, as one of the major issues is to to find new life forms outside of Earth, extraterrestrial life. So is it possible to combine nanotechnology, space, and biology to help solve this problem?
Why would you want to go out of the planet? There's a lot of problems to solve here. It's an interesting question. I think, at least from my perspective, I think as one of the speakers earlier on said, you never say never. There are always possibilities, and I do believe that there are distinct applications that nanotechnology would have in cosmology, but one that hopefully somebody like you would be able to sort of really see through it in terms of what those specific things that needs to be done. But I would strongly urge you to focus on problems of the planet right now.
Thank you.
Thank you.
Over here?
Good afternoon, speakers. I'm Kai Sing from Tampines Junior College. My question today is regarding the production of drugs like heparin. Do you think that instead of extracting the drug from pig intestines, do you think it's possible to synthesize them using transgenic organisms, bacteriums?
Yeah, that's a very good question, and let me put it in context. The field of glycobiology, if you use that as an example, when you compare to where, sort of glycomics, hence where proteomics is, not too long ago, the way we were able to make insulin was to isolate insulin from pigs. So heparin is isolated from pigs right now because what we have been able to do in glycobiology, even though this has been a sort of an important frontier, a fairly recent field in its explosion, it is where genomics and proteomics were like 20 years ago. We've been able to read the code, which is sort of what you saw, but we've not been able to write it, if you will. There are an important problem for the future is those that could crack the code of what is the principle behind polysaccharide synthesis. We still do not have the answers to that. Until that happens in a much more robust way and to be able to scale it up at the commercial level, it is going to be fairly difficult. Having said that, it's not that there aren't technologies that are out there that are able to make them, but they aren't at a level and scale that is similar to where you can produce them in large amounts for pharmaceutical production consumption.
Thank you.
We definitely need more chemists. This kind of problems can be tackled, I think, by synthetic chemistry, and the new branches where biology and chemistry come together holds a lot of promise. So I want to encourage many of you to go into that area. I know that many people hear about life sciences, and we probably have too many people in life sciences. I personally feel that a lot more people need to go into chemistry because chemistry is a backbone for pharmaceuticals industry.
We have a young man here.
Professor Ying, I have a question about the capsules for controllably releasing insulin. I'm a little bit skeptic about the word of controllably releasing insulin because, as you know, the problem is death of beta cells, and we need to accumulate the pool of beta cells in order to heal diabetes. Now, how these capsules are really controllable in terms of the sustainable release? Could you answer this question?
We're not dealing with those cells when we do control release. We're simply just introducing the insulin by oral or nasal passages. Okay, we're not trying to regenerate any cells in this process. Yeah.
But this is the problem, that you need to make some control of this process. Otherwise, it's not better than the regular injection of insulin.
No. Okay, there are things that people are trying to do to try to regenerate the pancreas. Okay, and all the beta cells, etc. That's a completely separate topic. Okay, what we try to do in different areas of research is there are things that engineers and chemists can do. For example, in developing new materials for drug delivery systems. Then we try to tackle those problems that we know exist and has a certain solution. We're trying to improve that solution, for example, by avoiding the need for detecting the blood glucose level and then injecting insulin, by having a very clever insulin delivery system. Trying to regenerate tissues and organs is a very, very long-term goal, and we are also doing some of that, but it is not something that we have reached a solution yet. It is a very important goal, but it will take a lot more time to get there.
Okay, thank you.
Thank you. Anyone else?
Okay. Hi, I'm Melvin. I'm from Republic Polytechnic, currently taking Diploma in Pharmaceutical Sciences. I have a question to Professor Jackie. Okay, here is a question. Based on your explanation regarding how nanoparticles can be used to treat cancer cells, as cancer cell has a low pH just now based on your explanation, therefore the nanocomposite will degrade in acidic condition and the drug will be released. But what we know that in stomach, it also has gastric acid, which is acidic. Thus, will the drug also be degraded in the stomach, even it hasn't reached the target site of cancerous cell? Thank you.
So this is a very common problem with standard drug delivery system. Usually they are also coated by something, coated by a material that will allow you to avoid being degraded by the stomach acid. This is what most system has to overcome that problem. So those material already exist, yeah.
So is it like using the enteric coating, isn't that right?
Yeah, there are different approaches to doing this, and so you have to escape the, being degraded by the stomach acid, and then you will go into the systemic circulation. Okay,
thank you. Anyway, I have a dream to become chemist, so no worries.
Yes. And I should say that we don't trivialize the drug delivery system for targeted delivery of cancer. A lot of glycobiology that Ram was talking about also are utilized because certain cancer will have overexpression of certain receptors, and those are being used also for targeted delivery.
Okay, thank you.
Please.
I'm Ayman Amin, student at IBN. I want just to ask about the commercialization of the new technological advancements. Usually it's a problem, especially in developing countries. So from your experience, how does it take, or what does it take to get to a successful spin-off of the technologies that has been done in certain research institute in emerging technologies like biotechnology and nanotechnology?
How are you successful at creating a spin-off?
Is your question how you spin technologies off? I'm just trying to understand that we were making sure.
That usually it's a problem to have spin-offs or to convert certain scientific research into a company that can just produce it commercially. So I just mean from your experience, what the obstacles or the hurdles that you have faced in such a process?
I think there are several. I know at the end of the day, success comes after a lot of failure more often than not. You know, one of the standard challenge an individual faces is, the analogy uses, anytime you have a technology, it's like a hammer. You think that hammer can hit every nail, and you start thinking of hitting things that you shouldn't be hitting. So from my perspective, one of the key things that really needs to come together is, depending on what the problem you're trying to solve, first is making sure the technology is robust in a proof of principle setting. So you need to make sure that whatever the proof of principle is solid, it's rigorous, and it's viable, in that it's not, it worked once, it didn't work a few times, it worked in this condition, it didn't work in those conditions, etc. I think the second is, this is where it needs to really be thought through carefully, in that it's the meeting of this technology, science, with the commercialization, in the sense that what the commercial application is going to be. It has to be driven by the application. So you frame it around the application and bring the technology then to see, is it a viable business model? So how all these elements come together is not easy. And very often people think, well, I have something, it's going to be useful, I'll start, and hopefully we'll find our way. Absolutely, it's important to have passion and persistence to be able to go after your dreams that way, but be pragmatic in terms of how, when you think about the sort of the translation or the transition of the technology from the lab into an application, the melting of the commercial application, the robustness of the technology, and how you therefore determine the business model, the mix of all those are key ingredients to at least ensure that it doesn't fail. There are several reasons things cannot work, but you have to make sure that at least the right ingredients are there to start the process.
Thank you. Thank you. Is there any other question here? There's one here. Please, you have the micro? Okay, that's okay.
Hi, I'm Elsa from Hwa Chong JC. This is a question directed to Professor Jackie. I really admire your insulin releasing mechanism. I think it's amazing. That's the kind of thing that makes me want to go into research. This is a question. You've talked about healing bone fractures through nanocomposites and about drug delivery through oral and nasal passages. But I'm asking, is it possible to actually improve the lives of people who are undergoing chemotherapy by localizing these nanomolecules as a system of drug delivery? So it's more about localizing the dosage and the effects of the chemo drugs so that it doesn't spread throughout the body. Is that a viable option?
We have developed some materials that has a combination of properties that will allow us to do targeted delivery for cancer that I mentioned earlier. It is pH responsive, it's thermal responsive, so it will only work in the body temperature. It will only work at the cancerous tissues and tumors. And also it will target certain receptors associated with overexpression of certain receptors in the body due to the cancer site. And what we have found is that when we package these materials in the appropriate nanoparticles, we can actually use a smaller dosage to kill more of the cancerous cells. So this is very important because first we have it targeted, so we minimize the systemic effect. Secondly, we can use less amount of drugs to kill the same number of cells. Okay, so we can basically introduce a much smaller dosage to do this. So we are very actively working in this area. And it really requires people with a very disciplinary approach to do this because the material involves a lot of polymer chemistry and synthesis. We need people with some pharmacy background, okay, and also biologists who understand the issues that we have trying to tackle with dealing with certain type of cells. Okay? So those things are all doable and we are very actively working on this. But different types of cancer have different issues. And I emphasize the diagnosis as something that was very important early on because many of you know if cancer is detected beyond the 3rd stage, it is really, really very difficult to cure completely. Okay, so this is why diagnosis and treatment, both areas need major advances. Okay.
So we have time for one last question from the audience.
Yeah, so the nanoparticles can be used for both diagnostics as well as therapeutic purposes. But can you please comment on the toxic effects of nanoparticles? Because we really don't know, a lot of different kinds of nanoparticles are there. What happens once it goes to the cellular machinery inside the body?
So the materials that we introduce into our body for drug delivery application or for tissue engineering applications all have to be made of polymers that are biocompatible and biodegradable for drug delivery systems especially, okay? Because if it's not degradable, it will accumulate in the body. So inorganic materials, even if they're non-toxic, it is really an issue because they tend to accumulate in organs like liver, lungs, and this is a major issue. But what we are doing for drug delivery systems are basically involved with biocompatible, biodegradable polymer. Those are the only things that I feel that in the next few years will have a chance to pass through FDA approval.
So do you think if the nanoparticle size is less than certain, maybe less than 20 nanometers or something, it can be used by the renal clearance mechanism to really clear out from the body?
Yes, many people believe that these very tiny particles, less than a certain size, can basically clear from the renal system, and therefore they should be safe. But I would say that all those things will need extensive tests and trials in order to be verified. And by the way, those that have been FDA approved as polymeric materials, usually they have to have very narrow molecular weight ranges. So these are things, you can be the same material, same composition that people think, but different molecular weight, and you will still have to go through extensive FDA approval. Okay.
Thank you.
All right. So maybe to wrap up, you guys had like some tough questions there. So I have an easiest one, but there's one come from Facebook, I believe. So there's someone asking, who has been your greatest scientific mentor in your life, and what was his or her most important advice? Maybe I can start with you, and then you with you.
I think one of the most important things for young people is to realize that a lot of people are there to help you pursue scientific areas, and especially in the research area. I think the most important people that have influenced my scientific career are my mentors, my PhD advisor and my postdoc advisor. I still remain in close touch with them. These are people that not only are great scientists, but wonderful human beings in that they share many perspectives on how they develop a career, what are the obstacles, what are the issues, and these are things that really are extremely valuable. It's beyond the scientific advice that I give that truly important to me. And I think that in Singapore, we need to create a system where we have such a mentorship relationship for young people as well as for people pursuing research studies. Okay?
I think Jackie couldn't have said it better. I think at the end of the day, it's important to be passionate about what you do, and therefore role models are important. And I think it's going to be fairly complex, especially when you're having interdisciplinary fields. There are going to be several different people with different backgrounds and expertise, but one that I think you have to follow your heart, really understanding what you're passionate about. And so with sort of that background, I was fortunate that my father was a scientist, so he was really an important role model for me to focus on my passion. And obviously my PhD mentor was somebody along the lines of what Jackie said. Made me ask the question, so what, with regard to the applications.
Okay, thank you very much. Thank you, both of you, for your time.